Hello. So I'm back to talk about some more quantum mechanics and going into the section of Griffiths, section 1.4, and this is about normalization. So, without having an idea that a wave function can be and actually needs to be normalized, this sort of statistical interpretation of quantum mechanics isn't going to be very useful. So this is just like, writing out that probability density that we did before. So if I look at the probability density of the Schrödinger equation over all space, so dx from negative infinity to positive infinity, so everywhere, and we're in x, so this is the spatial dimension, then that's going to equal 1. So what this means is that if I have a Schrödinger equation, psi, that is representing a particle, if I look at the probability density of that particle over all space, the probability of finding the particle at any point in all space is 1. So that just means that, yes, the particle does exist. So that has to be true. For a Schrödinger equation, we do have the necessity that it has to be normalizable. So in order to have a valid solution to the Schrödinger equation, that means that it does have to be normalizable, which means that we can't have something that, say, diverges, goes off into infinity. If we had this sort of diverging function, like we couldn't have something like psi would equal, say, x to the 3, because x to the 3, when x goes to infinity, this goes to infinity. So that would not be a solution to the Schrödinger equation, because if it's not normalizable, it can't actually represent a particle. Okay, but generally for our solutions to the Schrödinger equation, we will have something psi that's a function of x and t. So what if we have something that we normalize at t equals to 0? How do we know that it will stay normalized? So we normalize the function with our t equals 0, but what about, t equals 5, or t equals 50, or t equals infinity? How do we know that it stays normalized? So what we have here is an idea that, say, for our Schrödinger equation, the way that we would normally go about trying to normalize it is we would put out here a constant a, and this is a constant that would restrain our function to equal 1 over all space. And if we had a property of the Schrödinger equation is such that a is a constant, so a is not some function of t. So this is a property of solutions for the Schrödinger equation, is that if a were if A were to vary with different times, if that normalization constant were to vary